There is something about the ocean that invites us to wonder, to let go of the day and drift into its quiet depths. Tonight we'll explore ocean mysteries together, mysteries of the ocean that have captivated scientists and dreamers alike. Deep ocean mysteries that remind us how much beauty exists beyond what we can see. Before we begin, please consider subscribing to the channel for more sleep science explorations. It helps others find their way here too, one sleepy soul at a time. Now, there's nothing you need to do but relax, let your breathing slow, let your body settle into comfort. The ocean has been here for billions of years, patient and vast, and it will continue its ancient rhythms long after we've drifted into sleep. So close your eyes if you'd like, or let them soften their focus, and allow these gentle mysteries to carry you down, down, down into rest. In the western Pacific Ocean, there exists a crescent-shaped scar in the Earth's crust, a place where one tectonic plate slides beneath another in a process so slow and patient it measures itself in inches per year. The Mariana Trench extends downward for nearly 7 miles, and if you could lift Mount Everest from its foundation in the Himalayas and place it gently into this trench, the mountain's peak would still rest more than a mile beneath the ocean's surface. Down there, the world is utterly dark. The temperature hovers just above freezing, and the weight of all that water above presses down with a force that transforms everything it touches. It's a place that feels impossible, yet it exists, quiet and patient, holding its secrets in the cold. The ocean covers 71% of our planet's surface, a vast blue blanket that holds 99% of Earth's living space by volume, and yet we have directly observed only a fraction of it. Most of the ocean remains as mysterious to us as distant galaxies, its depths unvisited, its creatures unnamed, its landscapes unseen by human eyes. We send down robots with cameras and lights, their tethers stretching like umbilical cords into the dark, and they return with glimpses, fragments, beautiful impossibilities that remind us how much we don't know. The ocean is patient with our curiosity, revealing itself slowly, one small discovery at a time, while the vast majority of its territory continues its ancient existence entirely beyond our gaze, doing what it has always done in the quiet. The pressure at the bottom of the deepest trenches is more than 1,000 times greater than the pressure we experience here on the surface, where air moves freely and our lungs expand and contract without effort. A human body is mostly water, and water cannot be compressed the way air can, so the body itself wouldn't crumple like a submarine's hull. But the air spaces inside us, our lungs, our sinuses, the tiny pockets in our ears, would collapse instantly under that tremendous weight. Even if somehow those spaces could be filled with liquid instead of air, the body would still fail. Oxygen becoming toxic at such pressure, the nervous system overwhelmed by forces it was never designed to withstand. It's a reminder that some places exist beyond our physical form, beautiful in their inaccessibility, meant to be understood from a distance. When scientists needed a name for the very deepest parts of the ocean, those places below 20,000 feet where the seafloor drops away into trenches of impossible depth, they reached for mythology. Hadal, from Hades, the ancient Greek realm of the dead, a place beneath everything, dark and mysterious and removed from the world of light and life above. It seems fitting somehow, this connection between ancient stories and modern discovery, because these Hadal zones do feel like another world entirely. The creatures that live there move slowly through the darkness, their bodies built for pressure, their existence so different from ours that they might as well be alien. Yet they're not dead places at all, these Hadal zones. They're full of life, strange and beautiful, carrying on in the quiet deep. Light travels differently through water than through air, each wavelength absorbed at different depths as it penetrates down from the bright surface. Red light disappears first, filtered out within the first 30 feet, which is why everything underwater begins to look blue-green. Orange follows, then yellow, then green, until by the time you reach 600 feet, even the blue light has faded to almost nothing. But some light continues, dim and scattered, creating a twilight zone where vision still barely functions. At 3,300 feet, that last trace of sunlight finally gives up entirely, and the midnight zone begins. From here to the ocean floor stretches an eternal darkness, broken only by the living light that some creatures make themselves. It's a boundary invisible but absolute, separating the sun's influence from a world that exists entirely without it, a place where bioluminescence becomes the only stars. In the deep ocean, where food is scarce and temperatures hover just above freezing, something strange happens to the size of living things. Giant squids reach lengths of 40 feet or more, their tentacles stretching through the dark like living cables. Spider crabs grow leg spans of 12 feet, moving slowly across the seafloor like great delicate machines. Isopods, relatives of the pillbugs you might find under a rock in your garden, grow to 16 inches long in the deep, armored and ancient-looking. Scientists call this phenomenon deep-sea gigantism, and while the reasons aren't entirely clear, they think it might relate to longer lifespans in the cold, more efficient use of scarce food, or reduced predation pressure in the vast dark spaces. Whatever the cause, the result is creatures that seem to belong in fairy tales, beautiful in their exaggerated forms. Within the Mariana Trench, there exists a smaller depression, a place where the ocean floor drops away even farther, reaching a depth measured at 36,037 feet below sea level. This is the Challenger Deep, named for the HMS Challenger 2, the British survey ship whose crew first measured this extraordinary depth in 1951 using echo-sounding equipment. Only a handful of humans have ever descended to the Challenger Deep. Filmmaker James Cameron made the journey solo in 2012, and before him, in 1960, 2 men descended in a bathyscaphe called Trieste, spending 20 minutes on the bottom before ascending back to the world of light. What they found was not emptiness, but life. Small amphipods and fish somehow thriving in conditions that would destroy most living things, a testament to biology's remarkable persistence and creativity. Where tectonic plates pull apart on the ocean floor, seawater seeps down through cracks in the Earth's crust, approaching hot magma chambers below. The water is heated to extreme temperatures and becomes laden with minerals, sulfur compounds, metals, chemicals that would be toxic in most environments. This superheated water then shoots back up through vents in the seafloor, creating plumes that look like underwater chimneys or smokestacks, black or white depending on the minerals they carry. The water emerging from these vents can exceed 750 degrees Fahrenheit, hot enough to melt lead, yet just inches away the surrounding seawater remains near freezing, and around these vents thrives an entire ecosystem. Bacteria that metabolize sulfur instead of sunlight, tube worms growing 6 feet long with no mouth or digestive system, crabs and fish gathering in the warmth, life finding a way in the most unlikely place. If you could drain the ocean and walk across the exposed seafloor, you would find yourself traversing landscapes as dramatic as any on the continents above. The mid-ocean ridge system stretches for more than 40,000 miles, wrapping around the planet like the seams on a baseball. This underwater mountain range marks the boundaries where tectonic plates pull apart, where new ocean crust is constantly being born from volcanic activity. Some of these underwater mountains rise 13,000 feet from the seafloor, taller than many peaks in the Rockies, yet their summits still rest thousands of feet beneath the ocean's surface. We rarely think about these mountains because we can't see them, but they're there, vast and ancient, shaping ocean currents, creating habitats, existing patiently in the dark while we go about our lives in the thin, bright layer above. Along the ocean floor, in addition to the great ridge systems, stand thousands of seamounts, underwater mountains formed by volcanic activity that rise at least 3,000 feet from the sea floor but don't reach the surface. We've mapped perhaps a few thousand of these seamounts with any detail, but scientists estimate there may be more than 100,000 seamounts in the ocean, each one a potential oasis of biodiversity, a place where currents swirl and nutrients concentrate and life gathers in abundance. These mountains exist in darkness, their slopes covered with corals and sponges that filter the water, their peaks providing habitat for fish and other creatures. Most have never been visited by humans, never even been fully mapped. They continue their patient existence, anchors in the current, entirely indifferent to whether we know about them or not, holding their ecosystems in the quiet deep. Between the continental margins and the deep ocean trenches stretches the abyssal plain, vast underwater prairies of soft sediment accumulated over millions of years. These plains are among the flattest places on Earth, their gentle topography interrupted only occasionally by seamounts or scattered rocks. The abyssal plains cover roughly 40 to 45% of the ocean floor, which translates to about 30% of our entire planet's surface, an area larger than all the continents combined. Down there, the temperature stays constant near freezing, the pressure is immense, and food drifts down from above like slow snow, the remains of dead plankton and other creatures settling endlessly through the water column. Life on the abyssal plain moves slowly, methodically, creatures adapted to scarcity and patience, existing in a world that operates on entirely different timescales than the bright surface above, where everything feels rushed and urgent. In the most extreme environments of the deep ocean, near hydrothermal vents, in the cold seeps where methane bubbles up from the seafloor, in the high-pressure darkness of the deepest trenches, scientists have found bacteria that challenge our understanding of what life can endure. Some of these microorganisms can survive intense radiation, extreme temperatures both hot and cold, crushing pressure, and the complete absence of sunlight. When researchers exposed some deep-sea bacteria to conditions similar to the vacuum of space, they survived. This discovery has profound implications for the possibility of life beyond Earth, suggesting that biology might be far more resilient and adaptable than we once imagined. If life can thrive in the harshest environments of our deep ocean, perhaps it can exist in the subsurface oceans of Europa or Enceladus, those distant moons where water moves beneath ice in eternal darkness. Between 650 and 3,300 feet beneath the surface exists a layer called the mesopelagic zone, or the twilight zone, where the last traces of sunlight create a dim blue twilight before giving way to complete darkness below. Recent research using advanced acoustic technology has revealed that this zone contains astonishing amounts of life, possibly 10 times more fish biomass than we previously estimated. Small fish, lanternfish mostly, gather in enormous numbers in the twilight zone during the day, then migrate upward at night to feed in the more productive waters near the surface. This daily migration, involving perhaps billions of tons of fish moving up and down through the water column, represents one of the largest movements of biomass on the planet, a commute that happens every single day in the ocean's middle depths, largely invisible to us on the surface. Along the continental margins, where the seafloor begins its descent from the shallows to the abyss, great canyons cut through the rock and sediment carved by underwater avalanches and sediment flows over millions of years. The Monterey Canyon off the coast of California plunges more than 2 miles deep and stretches over 75 miles long. The Jemtchug Canyon in the Bering Sea is even larger, over 60 miles wide at its mouth. These underwater canyons create unique habitats, their steep walls covered with corals and sponges, their depths providing refuge for deep-sea creatures. Currents accelerate through these canyons like wind through mountain passes, bringing nutrients from the deep ocean up to the shallower waters, supporting abundant life. Yet because they're underwater, hidden from casual view, most people don't know these grand landscapes exist, these vast carvings in the earth that rival anything we see on land. In the midnight zone, where sunlight never penetrates, where darkness is absolute and permanent, an extraordinary adaptation has emerged: the ability to create light from living chemistry. Bioluminescence, the production of light through biochemical reactions within an organism's body, has evolved in the vast majority of deep-sea creatures. They use this light for different purposes, some to attract prey, dangling glowing lures in front of their mouths, some to communicate with potential mates, flashing specific patterns like a biological Morse code, some to startle predators or to camouflage their silhouettes by matching the faint light from above. The deep ocean is not actually dark in the way we imagine darkness. It's filled with living light, creatures glowing blue and green and sometimes red, creating a slowly changing constellation that moves through the water, a light show that continues every night in the deep, beautiful and strange and entirely necessary. The fact that so many different kinds of creatures developed the ability to produce light tells us something important about the deep ocean. It tells us that bioluminescence isn't just useful, it's essential. The chemistry of bioluminescence is complex, requiring specialized proteins and chemical reactions that had to evolve through countless generations of trial and error. Yet at least 40 different lineages of ocean creatures developed this ability separately, each finding their own biochemical path to creating light. Fish, jellyfish, squid, shrimp, bacteria, even some sharks, all solved the problem of darkness in similar ways, arriving at bioluminescence through entirely separate evolutionary journeys. It's a beautiful example of convergent evolution, life arriving at the same solution from different starting points, each lineage independently discovering that light is valuable enough in the deep darkness to be worth the metabolic cost of producing it. Perhaps the most famous example of bioluminescence in the deep ocean belongs to the anglerfish, that strange creature with enormous jaws and a glowing lure that dangles in front of its face like a fishing rod. But the anglerfish doesn't produce that light itself. Instead, a specialized bulb at the end of the lure provides a home for bioluminescent bacteria. The anglerfish provides the bacteria with nutrients and a safe place to live, and in return the bacteria produce light that attracts prey close enough for the anglerfish to strike. It's a partnership that has existed for millions of years, two entirely different forms of life working together in the darkness. The female anglerfish can control the brightness of the lure by restricting or increasing blood flow to the bulb, essentially dimming or brightening her living lamp as needed, a remarkable degree of control over her bacterial partners. In the 1960s, a scientist studying bioluminescence in a jellyfish called Aquaria victoria isolated the protein responsible for its green glow. He called it green fluorescent protein, or GFP, and at first it seemed like nothing more than an interesting curiosity, a way for jellyfish to create their gentle luminescence. But over the following decades, GFP became one of the most important tools in biological research. Scientists learned to attach GFP to other proteins, making them glow green, which allowed them to track those proteins through living cells, watching biological processes happen in real time. The researchers who developed GFP as a research tool won the Nobel Prize in Chemistry in 2008. It's a lovely reminder that curiosity-driven research into seemingly obscure questions, like why jellyfish glow, can lead to discoveries that transform our understanding of life itself, all because someone wanted to know about the light in the deep ocean. The cookie-cutter shark, a small deep-sea species rarely longer than 20 inches, has evolved an unusual form of camouflage. Most of its underside is covered with photophores, light-producing organs that glow with a soft blue-green light. When the shark swims in the twilight zone, where faint sunlight filters down from above, these photophores match the intensity of the light coming from above, effectively erasing the shark's silhouette when viewed from below. This is called counter-illumination, a kind of active camouflage that makes the shark nearly invisible to predators looking up from the depths. But the cookie-cutter shark has a darker collar around its throat that doesn't glow, creating a small dark shape that might resemble a small fish. Larger predators, seeing this apparent prey, swim up to investigate, and the cookie-cutter shark takes a quick circular bite from their flesh before disappearing back into the glowing twilight, leaving behind a distinctive cookie-shaped wound. On certain beaches on certain nights, when conditions are exactly right, the waves begin to glow. Each breaking wave lights up with blue-green bioluminescence, and every footstep in the wet sand triggers a burst of living light. This phenomenon, called a bioluminescent bay or phosphorescent bay, is created by tiny single-celled organisms called dinoflagellates, present in such high concentrations that every movement through the water triggers their defensive light response. The dinoflagellates produce light when agitated, possibly to startle small predators or to attract larger predators to eat whatever is disturbing them. Whatever the evolutionary reason, the result is magical. Waves that glow, water that sparkles with every movement, kayak paddles leaving trails of blue light in the darkness. It's one of the ocean's most beautiful mysteries, this living light created by organisms too small to see individually, yet visible in their millions as a gentle glow against the night. In the deep ocean where permanent darkness rules, some fish have evolved their own headlights. Species like the flashlight fish and the spookfish have organs called photophores located just below their eyes, containing bioluminescent bacteria that produce a steady beam of light. The fish can control these light organs, covering them with a dark membrane when they want to move through the water unseen, then uncovering them to illuminate their surroundings, looking for prey or identifying potential mates. It's remarkably similar to how we use flashlights to navigate in darkness, evolution arriving at the same practical solution through millions of years of trial and error. The light allows these fish to see in a world without sunlight, to hunt and avoid being hunted, to navigate through the vast darkness with small beams of living light that cut through the black water like tiny searchlights. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, an almost incomprehensible number, each star a sun with its own story burning across light years of space. And yet the ocean contains so many more bioluminescent bacteria that the comparison becomes almost meaningless. A single liter of seawater might contain billions of microbes, and the ocean holds roughly 1.3 billion cubic kilometers of water. Scientists estimate the total number of bioluminescent bacteria in the ocean to be around 10 billion trillion. That's 10 followed by 22 zeros. These bacteria outnumber the stars in our galaxy by trillions of times over, each one a tiny living light, most glowing in the deep ocean where no human eye will ever see them. It's a humbling thought, this vast, invisible constellation of bacterial light that exists beneath the waves, so abundant that it makes the stars seem scarce. Every spring, usually between March and June, something extraordinary happens in Toyama Bay on the western coast of Japan. Millions of firefly squid, each one only about 3 inches long, migrate from the deeper waters where they spend most of their lives up to the surface waters near shore to spawn. The squid are covered with photophores that produce a vivid blue bioluminescence, and when millions of them gather together in the night water, the bay lights up with an ethereal blue glow. The squid use their bioluminescence to attract mates and possibly to confuse predators, flashing and pulsing in coordinated patterns. Fishermen have harvested these squid for centuries, and tourists now come from around the world to witness the phenomenon. After spawning, the squid die, their brief lives ending in a final display of light, their bodies sinking to the sea floor while the next generation drifts away as tiny larvae into the dark water. In the deep ocean, where escape is often impossible in the vast open water, some small creatures have evolved an unusual defense mechanism. When threatened by a predator, they produce bright bioluminescent flashes that effectively say, "Something interesting is happening here." These flashes can attract even larger predators that might eat the creature's attacker, turning the tables on the original threat. It's sometimes called the burglar alarm strategy, and it's surprisingly common in deep-sea creatures. A small shrimp being chased by a fish might produce a burst of bright light, and that light might attract a larger fish that eats the smaller predatory fish, allowing the shrimp to escape in the confusion. It's a risky strategy. The light might just make the prey more visible. But in the darkness of the deep ocean, where options are limited, calling for help by literally illuminating the situation sometimes works, a desperate signal in the dark that occasionally saves a life. There exists a small jellyfish, Turritopsis dawni, barely a quarter-inch wide, that has earned the name immortal jellyfish for its remarkable ability to effectively reverse its aging process. When this jellyfish experiences stress, injury, starvation, temperature changes, or simply reaches the end of its normal life cycle, it can revert back to its juvenile polyp stage, essentially transforming from an adult back into a juvenile form. The polyp then grows and develops into a new adult jellyfish, and this cycle can theoretically repeat indefinitely. It's as if a butterfly could transform back into a caterpillar and then into a butterfly again, over and over. This doesn't make the jellyfish truly immortal. They can still die from disease or predation, but it does mean they've bypassed one of the fundamental rules of biology as we understand it. Scientists are studying these jellyfish carefully, trying to understand the cellular mechanisms that allow this transformation, hoping that understanding might someday tell us something about aging in other organisms. In the deep ocean, where light is scarce and every photon matters, the giant squid has evolved the largest eyes of any known creature on Earth. These eyes can measure up to 10 inches in diameter, roughly the size of a dinner plate, with lenses as big as oranges. Such enormous eyes aren't necessary for seeing in bright light, but in the deep twilight zone where the giant squid lives, large eyes provide a crucial advantage. They gather more of the scarce light available, allowing the squid to see the silhouettes of predators like sperm whales against the faint glow from the surface above, or to detect the bioluminescence of potential prey. The giant squid's eye represents evolution solving a specific problem: how to see in near-total darkness, with a straightforward solution. Make the light-gathering organ as large as physically possible. The result is an eye that looks almost alien, beautiful in its scale and purpose, perfectly adapted for a world of permanent twilight. Despite its ominous name, the vampire squid is actually one of the gentler creatures of the deep ocean. It's not a true squid, but rather represents its own unique order of cephalopods, an ancient lineage that has existed largely unchanged for hundreds of millions of years. The vampire squid got its name from the web-like membrane that connects its 8 arms, which resembles a vampire's cape when the creature draws its arms up around its body in a defensive posture. But far from being a fearsome predator, the vampire squid feeds primarily on marine snow, the constant rain of dead plankton, fecal matter, and other organic debris that drifts down through the water column. It uses 2 specialized retractile filaments to collect this material, then passes it to its arms, which have small sucker-like structures that help move the food to its mouth. The vampire squid lives in the oxygen minimum zone where most creatures cannot survive, moving slowly through the dark, peacefully collecting detritus, its dramatic name entirely at odds with its quiet lifestyle. The blobfish has become something of an internet celebrity for its unfortunate appearance when brought to the surface, a gelatinous, sad-looking mass that barely resembles a fish at all. But this appearance is misleading. At the depths where the blobfish normally lives, between 2,000 and 4,000 feet down, the pressure is 60 to 80 times greater than at sea level. The blobfish's body is designed for these conditions, with minimal muscle mass and a gelatinous consistency that's slightly less dense than water, allowing it to float just above the seafloor without expending much energy. At depth, the blobfish looks like a relatively normal fish, using its limited musculature to gulp down prey that drifts nearby. But when brought rapidly to the surface, the dramatic decrease in pressure causes the fish's body to expand and distort, like a balloon filled with gel, creating that unfortunate blobby appearance. It's a reminder that creatures adapted for extreme environments often don't translate well to ours. In the deep twilight zone swims one of the ocean's most unusual fish, the barrelly, with a head that looks like it belongs in science fiction. The top of its skull is a transparent dome filled with clear fluid through which you can see directly into the fish's head. Inside this dome are 2 tubular eyes, bright green and pointing upward, designed to detect the faint silhouettes of prey against the dim light from above. What makes these eyes even more remarkable is that they can rotate. The fish can shift them from looking upward to looking forward, allowing it to track prey as it moves into position to eat. The 2 dark spots on the front of the fish's face that look like eyes are actually its nostrils. The transparent dome probably protects the barrelly's sensitive eyes from the stinging cells of jellyfish whose tentacles it steals prey from. It's a fish that seems impossible, a reminder of how creative evolution becomes when solving the problems of life in the deep ocean's strange conditions. The goblin shark, a rare deep-sea species that looks like something from prehistoric times with its long flattened snout and pink-grey coloration, possesses one of the most unusual feeding mechanisms in the ocean. When the shark detects prey, probably using electromagnetic sensors in its long rostrum to sense the electrical fields produced by other animals, it can rapidly extend its jaws forward from its head. This happens so quickly that high-speed cameras were needed to fully capture the movement. The jaws shoot forward several inches, the teeth grab the prey, and then the jaws retract back into the normal position, all in a fraction of a second. This adaptation allows the goblin shark to capture prey that might otherwise escape, extending its reach beyond what its body shape would normally allow. The mechanism is possible because the shark's jaw is loosely connected to its skull, suspended by ligaments that can stretch suddenly when specialized muscles contract, creating this bizarre extendable mouth that seems to appear from nowhere. Swimming in the deep ocean, usually between 400 and 4,000 feet, lives a shark that looks remarkably similar to sharks that existed when dinosaurs walked on land. The frilled shark gets its name from the 6 pairs of gill slits that cross its throat, each one frilled at the edge, giving the shark an almost decorative collar. With its long eel-like body, primitive jaw structure, and around 300 backward-pointing teeth arranged in 25 rows, the frilled shark represents an ancient design that has persisted because it works well in the deep ocean environment. These sharks are slow-moving ambush predators, probably catching prey by quickly lunging forward and engulfing it whole. They can bend their bodies to strike from almost any angle, a flexibility unusual among sharks. Seeing a frilled shark is like looking back through time. a reminder that some solutions to the problems of survival are so effective that they need no improvement across millions of years and countless generations. In 2005, scientists exploring hydrothermal vents in the South Pacific discovered a new species of crab covered in what looked like blonde fur along its arms and legs. They called it the Yeti crab, and that fur turned out to be actually setae, hair-like structures that provide a home for bacteria. The bacteria living on these setae can detoxify the chemicals in the vent water and may also provide food for the crab, which scrapes them off and eats them. Essentially, the Yeti crab is farming, cultivating bacterial gardens on its own body. The crabs have been observed waving their hairy arms through the vent water, possibly to encourage bacterial growth, a behavior that looks almost like they're dancing in the hydrothermal plumes. It's a beautiful example of symbiosis, two completely different forms of life supporting each other in one of the ocean's most extreme environments, the crab providing a home and the bacteria providing food in return. Octopuses possess an intelligence that surprises researchers who study them, showing behaviors that suggest problem-solving abilities and even personality. In laboratory settings, octopuses have been observed opening child-proof containers to reach food inside, solving mazes, and even figuring out how to dim overhead lights by squirting water at them. In the wild, some species gather coconut shell halves or clamshells and carry them considerable distances, then assemble them into protective shelters. This is tool use, a behavior once thought to be limited to only a few species, including humans and some primates. Octopuses can also learn by watching other octopuses, and they seem to get bored, requiring environmental enrichment in captivity to stay healthy. What makes this intelligence even more remarkable is that octopuses are mollusks, more closely related to clams and snails than to the vertebrates that typically display such cognitive abilities. They represent an entirely separate evolutionary path to intelligence, showing that complex brains and problem-solving ability can emerge from very different starting points. In the tropical waters of Southeast Asia lives an octopus with a remarkable talent: the ability to change not just its color and texture like other octopuses, but to change its apparent shape and behavior to mimic other animals. The mimic octopus has been observed impersonating lionfish by holding its arms out in a fan pattern, flounder by flattening its body and hiding 6 arms while gliding with 2, sea snakes by hiding its body in a hole and waving 2 arms with black and white stripes, and many other forms. What makes this even more impressive is that the octopus seems to choose which animal to mimic based on the situation. When threatened by damselfish, which aren't bothered by sea snakes but avoid lionfish, it mimics a lionfish. This suggests not just the physical ability to mimic, but the cognitive ability to assess threats and choose appropriate responses. In a creature with a lifespan of only about a year, this represents a remarkable concentration of evolutionary innovation, turning the octopus into a living shapeshifter. The mantis shrimp, despite its name actually a stomatopod rather than a true shrimp, possesses perhaps the most sophisticated visual system of any animal on Earth. Where humans have 3 types of color receptors in our eyes, mantis shrimp have 12, allowing them to see colors and polarizations of light that we can barely imagine. Their eyes move independently and can perceive depth with just one eye. But vision isn't the mantis shrimp's only superpower. They're also among the ocean's most fearsome predators. Some species have specialized front appendages that can strike out at speeds up to 50 miles per hour, creating a force of over 1,500 newtons. The strike is so fast that it creates cavitation bubbles in the water, and when these bubbles collapse, they produce a small shockwave and a flash of light, adding extra damage beyond the initial impact. This punch, relative to the shrimp's size, is like being hit by a bullet. The mantis shrimp uses this weapon to smash open the shells of prey or to defend its burrow from intruders, a tiny creature wielding remarkable power in the shallow tropical waters where it lives. On the abyssal plains, in the perpetual darkness miles beneath the surface, live creatures that look more like plump walking sausages than any animal we're familiar with. Sea pigs, despite their name, are actually sea cucumbers, relatives of sea stars and sea urchins. They move across the soft sediment on enlarged tube feet that work like legs, grazing on the seafloor for organic particles settled from above. Sometimes they occur in high densities. Submersible cameras have recorded hundreds of sea pigs in one area, all facing the same direction. apparently oriented to the current to maximize their food collection. Their bodies are pink and soft, almost translucent, with protrusions that help them sense their environment. They're perfectly adapted to their strange home, existing in a world of pressure and cold and darkness that would be instantly lethal to most creatures. Yet they persist, generation after generation, walking slowly across the abyss, doing what they've done for millions of years in patient obscurity. While the giant squid gets more attention, the colossal squid may actually be more formidable. Living in the deep waters around Antarctica, the colossal squid can reach similar lengths to the giant squid but is much heavier and more robust. What truly sets it apart are the hooks on its tentacles, sharp, swiveling hooks embedded in the tentacle clubs used to grab prey. These aren't just suckers like most squid have, but actual hooks made of keratin, the same material as our fingernails, and they can rotate to better grip struggling prey. Some colossal squid have been found in the stomachs of sperm whales with hooks measuring more than an inch long. The whale's skin often bears circular scars that match the spacing of the squid's hooks and suckers, evidence of battles that occurred in the pitch darkness of the deep ocean. Very few intact colossal squid specimens have been recovered. They live in some of the most remote and inaccessible waters on Earth. So much about them remains mysterious, including the full extent of their hunting capabilities. The deepest living octopuses, the Dumbo octopuses, get their name from the ear-like fins that protrude from the sides of their bell-shaped bodies, making them look like the Disney elephant when they flap these fins to swim. They live at depths between 9,800 and 13,000 feet, making them among the deepest living octopuses known. Unlike many octopuses that crawl along the bottom, Dumbo octopuses swim above the seafloor, using their webbed arms and pulsing fins to move through the water in a way that looks almost graceful, almost whimsical, despite the crushing pressure and darkness of their environment. They feed on snails, worms, and other creatures they find on or near the seafloor, gulping them whole since they lack the ink sac and beak of shallower water octopuses. Several species of Dumbo octopus have been identified, but they're difficult to study because of the depths at which they live, and much about their behavior and life cycle remains unknown, these small, soft creatures doing their gentle swimming in places few humans will ever visit. Despite being a shark that can grow to 18 feet long and weigh over a ton, the megamouth shark was completely unknown to science until 1976, when one became entangled in the anchor of a US Navy research vessel off Hawaii. Since then, only a few dozen confirmed sightings have been recorded worldwide. The megamouth is a filter feeder, swimming with its enormous mouth open to strain krill and other small creatures from the water, similar to how baleen whales feed. It has bioluminescent tissue around its mouth, possibly to attract prey in the deep waters where it spends its days. The shark appears to undergo daily vertical migrations, following layers of krill and plankton that rise toward the surface at night and descend to deeper water during the day. The fact that such a large shark remained undiscovered for so long and remains so rarely seen reminds us how vast and unexplored the ocean truly is. How many large creatures might exist out there in the blue water still unknown to science? Before underwater microphones called hydrophones became common, people assumed the ocean was a silent world, the water too dense for sound, the creatures too primitive for communication. But the opposite is true. The ocean is full of sound, a constant symphony of biological and physical noises. Whales sing songs that can last for hours and travel thousands of miles. Fish grunt and croak using their swim bladders. Snapping shrimp create sounds so loud they can interfere with sonar. Ice groans as it cracks and shifts. Waves crash above, creating a hissing static that penetrates down through the water. Earthquakes rumble across the seafloor. Even the sound of rain falling on the surface creates a distinctive patter that can be heard from below. Sound travels much farther and faster in water than in air, and many ocean creatures rely more on sound than sight to navigate, communicate, and find food in the vast blue space. The ocean has never been silent, we just weren't listening carefully enough. Sound moves through water almost 5 times faster than through air, and it carries much farther, especially at certain depths where temperature and pressure create sound channels that can propagate noise across entire ocean basins. Whales have evolved to take advantage of this. producing sounds at frequencies that match these deep sound channels. A blue whale's call, produced at around 180 decibels, loud enough that if you were nearby in the water it could theoretically kill you, can theoretically be heard by other whales hundreds or even thousands of miles away. Before modern shipping filled the ocean with engine noise, whale songs probably traveled even farther. Scientists studying whale communication have recorded individuals separated by entire ocean basins responding to each other's calls, carrying on conversations across distances that seem impossible, these massive animals using the ocean itself as a kind of amplification system to stay in touch across the vast blue emptiness. Male humpback whales produce some of the most complex acoustic displays in the animal kingdom, songs that can last up to 20 minutes and then repeat for hours on end. What makes these songs even more remarkable is that they change over time. All the male humpbacks in a population sing roughly the same song in a given season, but the song slowly evolves, new phrases appearing and becoming popular, old phrases disappearing or changing. By the next breeding season, the song has transformed into something different, though still recognizable as related to the previous year's version. Whales from different populations sing different songs, but occasionally phrases from one population's song will appear in another population's song, suggesting the whales are learning from each other. Scientists aren't entirely sure why humpbacks sing these complex songs, probably to attract females or to compete with other males, but the songs represent a form of cultural transmission, knowledge passed not through genetics, but through learning and imitation. Since the 1980s, researchers using underwater microphones to track submarines noticed something unusual, a whale call at 52 Hz, a frequency higher than the usual 15 to 25 Hz of most baleen whales. This call has been tracked across the Pacific for decades, always alone, never accompanied by the calls of other whales. Media dubbed it the loneliest whale in the world, suggesting it was calling at a frequency other whales couldn't hear, forever unable to communicate with its own kind. However, more recent research suggests the story might be more complicated. 52 Hz is within the hearing range of other whales, and this individual's migration patterns are similar to other baleen whales, suggesting it's not entirely isolated. It might be a hybrid of two species, or simply an individual with an unusual voice. Still, the image of a lone whale calling out in a frequency slightly off from the rest resonates with us. This creature moving through the vast ocean producing sounds that mark it as different, whether lonely or not. Sperm whales live in matriarchal family groups called clans, consisting of related females and their young. These clans stay together for life, hunting together, raising calves together, moving through the ocean as a tight, social unit. And each clan has its own vocal dialect, a specific pattern of clicks used for communication. These dialects are so distinct that researchers can identify which clan a whale belongs to just by listening to its vocalizations. Different clans living in the same ocean may have completely different dialects, and clans with similar dialects tend to associate with each other, avoiding clans with different vocal patterns. This suggests that sperm whale culture is passed down through generations, learned rather than inherited, with each clan maintaining its own traditions and identity. Young whales learn their clan's dialect from their mothers and aunts, becoming part of a vocal tradition that may stretch back hundreds of years. The pistol shrimp, also called the snapping shrimp, is only about 2 inches long, but it produces one of the loudest sounds in the ocean. The shrimp has one oversized claw that can snap shut so quickly that it creates a cavitation bubble, a tiny void in the water caused by the rapid movement. This bubble then collapses almost instantly, and when it does, it creates a tiny shock wave and a sound that can exceed 210 decibels, louder than a gunshot measured underwater. Even more remarkable, the collapse of the bubble generates temperatures that briefly reach around 8,000 degrees Fahrenheit, nearly as hot as the surface of the sun, though only for a fraction of a second in an incredibly tiny space. The shrimp uses this bubble gun to stun prey and to communicate with other shrimp. In some places, pistol shrimp are so numerous that their collective snapping creates a background noise that interferes with sonar and underwater communication systems, these tiny creatures filling the ocean with explosive sound. Many fish species produce sounds using their swim bladders, the gas-filled organs that help them control buoyancy. By vibrating muscles around the swim bladder, fish can create a range of sounds: grunts, croaks, buzzes, and hums. Some fish drum against their swim bladders using specialized muscles that can contract up to 1,000 times per second, creating sounds used for courtship, territorial disputes, or communication within schools. The toadfish produces a foghorn-like sound by vibrating its swim bladder, and male toadfish will call for hours during breeding season, their low-frequency groans carrying through the water. Oyster toadfish have been recorded at 95 decibels, and coastal residents sometimes complain about the constant humming sound of courting fish during summer nights. The ocean is full of fish conversation, overlapping calls and responses, warnings and invitations, a constant chatter in frequencies we rarely think to listen for. When icebergs break off from glaciers and float into warmer water, they begin the slow process of melting and eventually breaking apart. As this happens, the ice shifts and cracks, producing sounds that range from sharp cracks to deep groans. But some icebergs produce something more unusual: harmonic tremors, sustained musical notes that can last for hours or even days. These sounds occur when the iceberg's melting creates a sustained vibration, possibly from water flowing through cracks and channels in the ice, or from the ice itself resonating as it shifts. Hydrophones have recorded these harmonic tremors at various frequencies, sometimes sounding almost like singing, a deep thrumming note that rises and falls as the ice continues its transformation from solid to liquid. It's the sound of deep time compressed into a human-perceivable moment, ancient ice that fell as snow thousands of years ago finally returning to the ocean with a long musical goodbye. In 1997, hydrophones operated by NOAA detected an extremely powerful ultra-low frequency sound in the South Pacific. The sound, which they nicknamed the bloop, was loud enough to be picked up by sensors more than 3,000 miles apart. Its frequency signature didn't match any known man-made sound source, and it was too large in scale to be from any known animal, even a whale. For years, the bloop remained unexplained, subject to speculation and theories ranging from unknown giant sea creatures to underwater volcanic activity. Eventually, NOAA determined the sound's characteristics matched those produced by ice calving events, massive chunks of ice breaking off from Antarctic ice shelves and crashing into the ocean. The sound's loudness and frequency pattern fit well with large-scale ice breakup events. While perhaps less exciting than an unknown leviathan, the answer is itself remarkable. Ice breaking in Antarctica produces sounds loud enough to travel across thousands of miles of ocean. Each bottlenose dolphin develops a unique signature whistle early in life, a distinctive acoustic pattern that serves as its individual identifier. Dolphins use these signature whistles to announce their presence, to get the attention of specific individuals, and to maintain contact with group members when separated. Research has shown that dolphins can remember the signature whistles of individuals they haven't encountered in over 20 years, suggesting these whistles function very much like names. Mother dolphins whistle frequently to their newborn calves, apparently teaching them to recognize their mother's signature sound. Dolphins will also copy the signature whistles of other dolphins, apparently to address them directly, the equivalent of calling someone by name. This represents a level of referential communication rare in the animal kingdom. These intelligent marine mammals using learned sounds to refer to specific individuals, maintaining social bonds through personalized acoustic labels that endure across time and distance. In certain places on the ocean floor, denser water flows like a river through the surrounding less dense water, creating underwater currents with distinct boundaries that behave remarkably like surface rivers. These submarine rivers can be caused by differences in salinity or temperature that make the water denser, causing it to flow downslope along the seafloor. The Black Sea has an underwater river flowing through the Bosphorus Strait, carrying dense Mediterranean water down into the Black Sea's depths. This submarine river has its own riverbed, banks, and even flooding zones, and if it were on the surface, it would be the 6th largest river on Earth by volume. Underwater rivers also form around Antarctica, where extremely cold, salty water produced by sea ice formation sinks and flows along the continental slope. These dense water masses can travel for thousands of miles along the ocean bottom, carrying nutrients and affecting ocean circulation patterns, invisible rivers within the larger ocean. In the coldest polar waters, when sea ice forms on the surface, it excludes salt from the ice crystal structure, creating pockets of extremely cold, extremely salty brine. Sometimes this dense brine sinks through the water column in a stream, and because it's so cold, colder than the freezing point of the surrounding seawater, it causes the water around it to freeze. This creates a growing icicle extending down from the sea ice above, a tube of ice called a brinnicle. The brinnicle grows downward, sometimes reaching the seafloor in just a few hours. When it touches the bottom, the super-cold brine spreads out, freezing everything in its path. Starfish, sea urchins, any slow-moving creatures are frozen in place almost instantly. Time-lapse photography has captured this phenomenon, showing the brinnicle growing like a finger of ice reaching down through the water, leaving a trail of frozen death behind it. It's a reminder of how alien and hostile even Earth's oceans can be. Blue holes are circular underwater caves or sinkholes that appear as dark blue circles against the lighter shallow waters surrounding them. They form when limestone bedrock dissolves over thousands of years, creating caves that eventually collapse. Some blue holes, like Dean's Blue Hole in the Bahamas, plunge more than 600 feet straight down, their walls vertical or even overhanging. The water in blue holes is often stratified, fresh or brackish water near the top, dense salty water below, and sometimes a layer in between where the mixing creates strange visual effects. These holes often have limited water circulation, leading to low oxygen levels at depth and unique ecosystems adapted to these challenging conditions. Divers are drawn to blue holes because of their dramatic depths and cathedral-like interiors, but they're also dangerous. Poor visibility, strong currents, and easy disorientation have led to many diving fatalities. Blue holes represent the ocean reclaiming land, saltwater filling spaces that were dry caves during lower sea level periods. Unlike the black smoke events powered by volcanic heat, the Lost City hydrothermal field in the Atlantic Ocean is powered by a chemical reaction between seawater and the rocks of the seafloor. This reaction produces heat and creates fluids rich in hydrogen and methane but poor in metals and sulfur. The result is dramatically different from typical hydrothermal vents. Instead of black chimney structures, Lost City has soaring white towers made of carbonate minerals, some reaching 60 feet tall, that look like Gothic spires or melted candles frozen in place. The fluids emerging from these towers are warm but not extremely hot, around 100 to 160 degrees Fahrenheit, and have a high pH, making them alkaline rather than acidic. Despite these unusual conditions, the vents support thriving microbial communities that don't depend on photosynthesis or volcanic heat, but instead derive energy from the chemical reactions between rock and water. Lost City has been venting for at least 30,000 years and possibly much longer, these white towers growing slowly in the dark. At certain places on the seafloor, usually associated with salt deposits, extremely salty water seeps up through the sediment. This water is so dense that it doesn't mix with the surrounding seawater but instead pools in depressions, forming underwater lakes with distinct surfaces, shores, and even waves. These brine pools have a coastline where the normal seawater meets the ultra-dense brine, and the boundary is sharp enough that it reflects light and can be seen clearly by submersibles. The brine is often toxic to most life, extremely salty and often lacking oxygen, but bacteria thrive there, and sometimes creatures like mussels line the shore of these underwater lakes, living at the boundary between two liquid worlds. If a fish or crab ventures into the brine, it often dies quickly, sinking to the bottom of the underwater lake where its body may be preserved by the hostile conditions. These brine pools are among the ocean's strangest features, lakes within the ocean that cannot mix, maintaining their separate existence for thousands of years. In 2011, Swedish treasure hunters using sonar discovered an unusual circular formation on the floor of the Baltic Sea, about 300 feet below the surface. The formation appeared to be roughly 200 feet in diameter with what looked like straight edges and angular features, leading to speculation ranging from ancient structures to crashed spacecraft. Subsequent visits to the site revealed the object is made of rock, likely basalt, with a composition that includes limonite and goethite. Some geologists believe it's a natural glacial deposit, a piece of bedrock plucked up by glaciers during the Ice Age and deposited when the ice melted. The apparently geometric features might be fracture patterns in the rock or effects of erosion. However, the formation's origin remains debated. Some samples taken from the site showed unusual characteristics, and the perfectly circular shape is admittedly odd for a natural formation. It continues to generate interest from those who believe it might be something other than natural geology, while most scientists consider it an interesting but ultimately geological feature. Trapped in ice-like structures on and below the ocean floor lie massive deposits of methane hydrate, sometimes called methane ice or fire ice. These deposits form when methane gas, produced by bacteria breaking down organic matter in sediments, combines with water under the high pressure and low temperatures found on the deep sea floor. The result is a white substance that looks like ice but burns if you light it. Scientists estimate there may be more carbon stored in methane hydrate deposits worldwide than in all of Earth's coal, oil, and natural gas reserves combined. These deposits are stable under current conditions, but if ocean temperatures rise, the hydrates could destabilize and release massive amounts of methane, a potent greenhouse gas, into the atmosphere. Some scientists believe past releases of methane from hydrate deposits may have contributed to rapid climate change events in Earth's history. The deposits represent both a potential future energy source and a potential climate hazard, sitting quietly in the cold and pressure. Fishing nets lost or abandoned at sea become what marine biologists call ghost gear, and they can continue catching fish and other marine life for years or even decades. These nets drift through the ocean or snag on reefs, accumulating dead and dying creatures in a cycle that can persist until the net finally degrades. But something interesting also happens. The nets become artificial reefs, providing hard surfaces in the open ocean where algae can grow, where small creatures can shelter, where life can establish itself. Over time, a ghost net becomes its own traveling ecosystem, carrying fish eggs, larvae, and various organisms across ocean distances they might never otherwise traverse. Some nets have been recovered with entire communities living in them, corals, barnacles, and fish both dead and alive. It's a reminder of how persistent plastic and synthetic materials are in the ocean, how our debris becomes incorporated into marine ecosystems in ways both harmful and, strangely, sometimes productive, the ocean trying to make use of what we've left behind. Throughout the ocean, especially in limestone regions, submarine caves wind through the rock below the seafloor, and inside some of these caves hang stalactites and stalagmites identical to those found in dry caves on land. These formations can only grow in air from mineral-rich water dripping slowly over thousands of years, which means they formed during ice ages when sea levels were hundreds of feet lower and these caves were dry. When the ice melted and sea levels rose, the ocean flooded these caves, preserving the stalactites underwater. Divers exploring these submerged caves swim past formations that grew when their locations were part of the terrestrial world, beautiful mineral sculptures that now exist in the ocean's dark. The formations give scientists information about past sea levels and climate conditions. They also create surreal environments, swimming through rooms decorated with stalagmites that grew in an ancient absence of water now drowned in the returning ocean. Off the coast of Yonaguni Island in Japan, at depths of about 80 feet, lies a massive rock formation that has sparked debate for decades. The formation consists of what appear to be stacked platforms, flat surfaces, and straight edges, arranged in ways that some believe could only be artificial. Those who think it's man-made suggest it might be the remains of an ancient civilization, submerged when sea levels rose at the end of the last ice age around 10,000 years ago. Geologists who have examined the site generally conclude it's a natural formation. The local bedrock is sandstone that naturally fractures along parallel planes, creating straight edges and right angles. Water erosion could have enhanced these features. However, some details are harder to explain naturally, and the debate continues. Whether natural or artificial, the Yonaguni monument is striking. These seemingly architectural shapes underwater suggesting order and purpose whether they possess it or not, a reminder that nature can sometimes create patterns that look intentional. Seawater contains trace amounts of almost every element on Earth, including precious metals. Gold occurs in seawater at extremely low concentrations, roughly 0.01 to 0.1 parts per billion, but because the ocean is so vast, the total amount adds up to something astonishing. Scientists estimate there are approximately 20 million tons of gold dissolved in the world's oceans, worth trillions of dollars at current prices. However, extracting this gold is completely impractical with current technology. The concentration is so low that you'd have to process enormous volumes of water to recover even tiny amounts, requiring more energy than the gold would be worth. Several people have tried and failed to economically extract gold from seawater over the past century. So the gold remains there, dissolved and useless to us, but important to ocean chemistry, moving through the great cycles of water and rock, participating in the chemical reactions that make the ocean what it is, valuable but uncollectible, treasure that cannot be claimed. The megalodon was the largest predatory shark that ever lived, reaching lengths possibly exceeding 60 feet with teeth over 7 inches long. For nearly 20 million years, megalodons were apex predators in the ocean, feeding on whales and other large marine mammals. Then, about 3.6 million years ago, they disappeared from the fossil record. The reasons for their extinction aren't entirely clear. Climate change causing cooling oceans, loss of prey species, competition with newly evolved great white sharks, or some combination of factors. What's striking is how recently megalodons existed. 3.6 million years seems like ancient history, but it's remarkably recent in geological terms. Early humans' ancestors were already walking upright when megalodons still hunted in the ocean. The thought of such massive predators existing so recently reminds us that Earth's current biodiversity is just one snapshot in an ongoing story of change, species rising and falling over time. Ammonites, those spiral-shelled marine mollusks related to modern nautilus and squid, were among the most successful animals ever to live in the ocean. They first appeared around 400 million years ago and diversified into thousands of species, filling ecological niches throughout the ocean. Some were tiny, others grew several feet across. Their shells show incredible variety, smooth, ribbed, covered with spines or tubercles, coiled tightly or loosely. They survived multiple mass extinction events, bouncing back each time with new forms and adaptations. Then, 66 million years ago, the asteroid impact that killed the dinosaurs also killed the ammonites. Every single species went extinct, ending 300 million years of evolutionary success. We find their fossilized shells in sedimentary rocks worldwide, beautiful spirals that hold echoes of ancient oceans, reminders that even the most successful lineages can end suddenly, that nothing is guaranteed continuity no matter how long it has persisted. Long before the age of dinosaurs during the Paleozoic era, the ocean's apex predators were arthropods, relatives of modern scorpions, spiders, and crabs, but adapted for marine life. The largest of these were eurypterids, sometimes called sea scorpions, and some species grew to enormous sizes. Jaekelopterus rhenaneo reached lengths of possibly 8 to 9 feet, maybe even longer based on fragmentary fossils. These creatures had powerful swimming appendages, grasping claws, and possibly venomous stingers. They hunted in ancient seas for nearly 250 million years, from the Ordovician through the Permian periods. The thought of scorpion-like creatures this size swimming through the ocean seems almost impossible now, when the largest marine arthropods are crabs and lobsters, a fraction of that size. They represent a time when evolution experimented with body plans that no longer exist, when the ocean was ruled by creatures that would look alien to us now. Early in Earth's history, before plants and algae filled the ocean with oxygen, photosynthetic life may have looked very different. Some scientists have proposed the purple Earth hypothesis, suggesting that ancient microbes used a molecule called retinal instead of chlorophyll to capture sunlight. Retinal is purple, and organisms that use it exist today. Various species of archaea called halobacteria use retinal-based photosynthesis, giving them a distinctive purple color. If these retinal-based organisms dominated early Earth, the biological sheen of life covering the surface would have been purple rather than the green we see today. This doesn't necessarily mean the ocean water itself was purple, but the dominant life forms on the surface, both on land and in the ocean, would have created a purple biological layer. Eventually, chlorophyll-based photosynthesis became dominant because it's more efficient, and Earth transitioned to the green world we know, but for potentially billions of years, life might have been purple. For much of Earth's early history, the ocean contained almost no dissolved oxygen. Life existed. Single-celled organisms thrived in this oxygen-free environment, but it was life completely different from what we know today. Then, around 2.4 billion years ago, cyanobacteria evolved oxygen-producing photosynthesis, and everything began to change. At first, the oxygen produced reacted with dissolved iron in the ocean, causing iron to precipitate out and fall to the seafloor, creating the banded iron formations we mine today for metal. This process continued for hundreds of millions of years, the ocean slowly absorbing oxygen, until finally, around 800 million years ago, oxygen levels in the deep ocean began to rise significantly. This oxygenation enabled the evolution of complex, multicellular life, animals with high energy needs that could only be met by aerobic respiration. The ocean transformed from an anoxic soup to a breathable environment, though that transition took longer than humans have existed, longer than mammals have existed, almost incomprehensibly slow change that remade the world. When cyanobacteria first began producing oxygen as a waste product of photosynthesis, they fundamentally changed Earth's chemistry. Oxygen is highly reactive, and for a long time, the oxygen produced by these bacteria immediately reacted with iron and other materials in the ocean and rocks. But eventually, around 2.4 billion years ago, the oxygen began to accumulate in the atmosphere and dissolved in the ocean, creating what scientists call the Great Oxidation Event. For organisms that had evolved in an oxygen-free world, this was a catastrophe. Oxygen was toxic to them. Many lineages went extinct or were forced into specialized environments where oxygen couldn't reach. But this event also opened the door to new forms of life that could use oxygen to extract far more energy from food. The evolution of complex life, including eventually all animals, was made possible by this transformation. The ocean changed from a reducing environment to an oxidizing one, a shift so fundamental that it defines Earth's history, marking the transition from a primordial world to one where creatures like us could eventually evolve. When a whale dies and its body sinks to the deep ocean floor, it becomes an oasis of nutrients in the desert-like environment of the abyss. The carcass goes through several stages of decomposition, each supporting different communities of organisms. First come the scavengers, hagfish, sleeper sharks, crabs, that strip the flesh in a matter of months. Then come organisms that colonize the bones, eating the remaining tissues and oils. Finally, bacteria that break down the lipids in the bones create sulfide-rich conditions similar to hydrothermal vents, supporting chemosynthetic bacteria that form the base of a unique food web. This final stage can last 50 to 100 years or longer, an ecosystem existing on the energy stored in whale bones. Over 400 species have been found associated with whale falls, some found nowhere else. A single whale's death supports life for decades in the deep ocean, one last generous contribution to the community that fed the whale during its life, a gift of sustenance that persists long after the whale has gone. The Greenland shark, living in the cold waters of the North Atlantic and Arctic Ocean, has the longest known lifespan of any vertebrate animal. Using radiocarbon dating of the eye lens, scientists determined that Greenland sharks don't reach sexual maturity until they're around 150 years old, and they can live for 400 years or more. A Greenland shark alive today might have been born before the American Revolution, swimming through the Arctic waters while human history unfolded in the world above. They grow extremely slowly in the cold water, reaching lengths of over 20 feet, moving through their environment with patient slowness. These sharks serve as a reminder that time operates differently in the deep ocean, that lifespans we can barely imagine are possible for creatures living in cold, stable environments with slow metabolisms. The oldest Greenland shark ever found was estimated to be around 512 years old, making it the oldest known individual vertebrate, a living link to centuries of ocean history. Throughout Earth's history, asteroids and comets have struck not just land, but also the ocean, which covers most of the planet's surface. These impacts create underwater craters similar to those on land, though they're harder to detect because they're covered by water and often filled with sediment. The Chesapeake Bay impact crater, now buried under sediment beneath the bay and surrounding areas, was created about 35 million years ago when an asteroid roughly 2 miles wide struck a shallow ocean covering what is now Virginia. The impact vaporized water, created enormous tsunamis, and left a crater roughly 50 miles wide. Similar underwater craters exist around the world, including one beneath the Gulf of Mexico called Chicxulub, formed by the asteroid that helped end the age of dinosaurs 66 million years ago. These craters remind us that Earth has been repeatedly struck by objects from space, and that the ocean, despite its vastness, offers no protection from cosmic impacts, just different consequences, massive waves instead of fire and blast, but catastrophic nonetheless. The ocean doesn't sit still. Water is constantly moving in a global circulation pattern driven by differences in temperature and salinity. Warm water near the equator flows toward the poles at the surface, carrying heat with it. As this water reaches the Arctic and Antarctic, it cools and becomes saltier through ice formation. This cold, salty water is denser, so it sinks to the deep ocean and flows back toward the equator along the seafloor, eventually upwelling in various locations to complete the cycle. This pattern, called thermohaline circulation or the global ocean conveyor belt, moves vast amounts of water through all the world's ocean basins. A drop of water that sinks in the North Atlantic might not return to the surface for 1,000 years, spending centuries slowly moving through the deep ocean's darkness. This circulation is crucial for regulating global climate, distributing heat and nutrients, and maintaining the ocean's chemistry. It's a slow, patient process operating on timescales far longer than human lifespans, the ocean's deep metabolism continuing regardless of what happens in the bright layer above. The ocean is Earth's primary heat distribution system, moving warm water from the tropics toward the poles and cool water back toward the equator. The amount of heat transported by ocean currents is almost incomprehensible. The Gulf Stream alone carries roughly 1.4 petawatts of thermal energy northward, equivalent to the output of about 100,000 large power plants running continuously. This heat transport moderates global climate, making northern Europe much warmer than it would otherwise be at that latitude, enabling agriculture and comfortable living in places that would otherwise be far colder. Changes in ocean circulation can therefore have dramatic effects on climate. Some scientists believe disruptions to the Gulf Stream contributed to rapid cooling events in the past. The ocean is constantly working to even out temperature differences across the planet, absorbing heat in the tropics and releasing it at higher latitudes, a global thermostat that operates silently and continuously, moving energy on scales that dwarf human capabilities. The Gulf Stream, that river of warm water flowing through the Atlantic Ocean, moves at a rate of roughly 30 million cubic meters per second at its maximum. That's about 100 times the combined flow of all rivers on Earth. This massive current, up to 60 miles wide and 3,000 feet deep in places, carries warm water from the Gulf of Mexico up along the eastern coast of North America and then across the Atlantic toward Europe. Ships sailing with the Gulf Stream can save time and fuel, while those sailing against it fight a current that can flow at speeds up to 5.6 miles per hour. Benjamin Franklin created one of the first maps of the Gulf Stream in 1770 based on information from whaling captains who had learned to avoid it when sailing west. The Gulf Stream has been flowing for millions of years, this great river in the ocean, moving water and heat and life, connecting distant shores through its continuous patient motion. For centuries, sailors told stories of monstrous waves appearing suddenly in the open ocean, towering walls of water that could dwarf even large ships. These stories were often dismissed as exaggerations or myths, until oceanographers confirmed that rogue waves, also called freak waves, are real. These waves can appear without warning, even in relatively calm seas, rising to heights of 80 or even over 100 feet. Unlike tsunami waves, which are caused by earthquakes or landslides, rogue waves form through complex interactions between wind, currents, and the natural patterns of ocean swells. Sometimes multiple wave trains converge at just the right moment, their energies combining to create a single enormous wave that persists for only minutes before dissipating back into the normal sea state. Satellite data has revealed that rogue waves occur more frequently than scientists previously thought, perhaps several times per day, somewhere in the world's oceans, these temporary giants rising briefly before sinking back into the endless motion of the sea. While surface waves are what we typically notice, the ocean experiences another kind of wave entirely, internal waves that form at the boundaries between water layers of different densities. These internal waves can be enormous, hundreds of feet tall, dwarfing any surface wave, yet they're completely invisible from above. They form along the thermocline, the boundary between warm surface water and cold deep water, and they move slowly compared to surface waves, sometimes taking hours to pass a fixed point. Internal waves are generated by tides flowing over underwater topography, wind patterns, or other disturbances, and they can affect everything from submarine navigation to the distribution of nutrients and plankton. Submarines moving at the wrong depth relative to an internal wave can experience sudden turbulence. These hidden waves represent energy moving through the ocean's interior, massive oscillations in the boundary between light and dark, warm and cold, happening constantly in the ocean's middle depths, where few humans ever venture to observe them directly. In certain areas of the ocean, oxygen levels drop so low that most fish and other mobile animals cannot survive there. These hypoxic zones, sometimes called dead zones, form when excess nutrients, often from agricultural runoff containing fertilizers, fuel explosive growth of algae. When these algae die and sink, bacteria decompose them, consuming oxygen in the process. If the water isn't mixing much with oxygen-rich water from above or nearby, oxygen levels can drop to near zero. The result is a zone where only specially adapted bacteria and some invertebrates can survive. Fish that enter these zones must quickly leave or suffocate. The number and size of ocean dead zones have been increasing due to nutrient pollution from human activities. The Gulf of Mexico has a large seasonal dead zone where the Mississippi River delivers nutrients from farmland throughout the central United States. These zones represent the ocean struggling with the burden of nutrients that would naturally be dispersed or locked in soil, now concentrated and overwhelming the system. The ocean contains swirling masses of water called mesoscale eddies, similar in some ways to atmospheric storms, but made of spinning water instead of spinning air. These eddies can be enormous, 60 or even over 100 miles across, and they can persist for months or even years, slowly moving across the ocean. Warm core eddies rotate clockwise in the northern hemisphere and contain water that's warmer than the surrounding ocean, while cold core eddies rotate counterclockwise and contain cooler water. These eddies trap water and whatever organisms are in it, transporting ecosystems across ocean basins. A tropical eddy moving north might carry warm water species far beyond their normal range. Eddies are important for mixing nutrients and heat throughout the ocean, creating three-dimensional structure in what might otherwise be relatively uniform water. Satellites can detect these eddies from space by measuring sea surface height. Warm eddies sit slightly higher than the surrounding water, while cold eddies sit lower, these spinning gyres visible from orbit as subtle bumps and depressions in the ocean's surface. The word thermohaline combines thermo for temperature and haline for salt, and it describes the deep ocean circulation driven by differences in these two properties. Cold water is denser than warm water, and salty water is denser than fresh water, so water that is both cold and salty sinks to the bottom of the ocean. This happens most dramatically in the North Atlantic and around Antarctica, where surface water cools significantly and becomes saltier through ice formation. This dense water sinks and begins flowing along the ocean floor, forming deep currents that eventually spread throughout the world's oceans. Meanwhile, warmer surface water flows in to replace the water that sank, creating a global circulation pattern. This circulation is crucial for distributing heat, nutrients, and dissolved gases throughout the ocean. It's also vulnerable to disruption. If melting ice sheets deliver enough fresh water to the North Atlantic, they could reduce the water's density enough to slow or stop the sinking that drives the circulation, with potentially dramatic effects on global climate. In places where the ocean is forced through narrow channels or around islands, tidal currents can flow with remarkable speed and force. The Bay of Fundy between Nova Scotia and New Brunswick has the highest tides in the world, with water levels changing by up to 50 feet between high and low tide. This creates tidal currents that rush through the bay's channels at speeds up to 10 miles per hour. Similar strong currents occur in other locations like the Pentland Firth in Scotland or the narrow channels in the Pacific Northwest. These currents represent significant amounts of kinetic energy, moving water that can be captured and converted to electricity using underwater turbines, similar to wind turbines but designed for the denser medium of seawater. Several experimental and commercial tidal power installations now operate in various countries, harnessing the predictable rise and fall of tides to generate renewable electricity, using the ocean's patient rhythm as a power source. Flowing continuously around Antarctica, the Antarctic Circumpolar Current is the only ocean current that circles the entire globe unobstructed by land. It's enormous, It transports roughly 134 million cubic meters of water per second, more than 100 times the flow of all the world's rivers combined, making it the largest ocean current by volume. The current is driven by the strong westerly winds that blow continuously around the Southern Ocean, and it plays a crucial role in global ocean circulation, connecting the Atlantic, Pacific, and Indian Oceans. This current also helps keep Antarctica isolated and cold by preventing warmer water from lower latitudes from reaching the continent. It creates a kind of fluid barrier, separating Antarctic waters from the rest of the world's oceans. The current extends from the surface to the ocean floor in many places, a vast river of water moving endlessly around the bottom of the world, channeling energy and heat and marine life in an endless circle. Every breath you take exhales carbon dioxide, and every car and power plant and industrial process adds more CO2 to the atmosphere. About 30% of all the carbon dioxide humans have released through burning fossil fuels has been absorbed by the ocean. The ocean acts as a carbon sink, with CO2 from the air dissolving into the surface water, then being transported to the deep ocean through the global circulation. This absorption has helped slow the rate of atmospheric CO2 increase and climate change, but it comes at a cost. When CO2 dissolves in seawater, it forms carbonic acid, making the ocean more acidic. This ocean acidification makes it harder for creatures like corals, mollusks, and some plankton to build their calcium carbonate shells and skeletons. The ocean is performing an enormous service by absorbing this carbon, but it's affecting the ocean's chemistry in ways we're only beginning to understand, the water becoming slowly more acidic as it works to buffer the atmosphere above. The ocean is a complex chemical soup containing at least trace amounts of every naturally occurring element. Besides the obvious water, hydrogen and oxygen, seawater contains dissolved sodium and chlorine that give it saltiness, plus magnesium, calcium, potassium, and many others. Even elements we think of as rare, like gold, platinum, and uranium, are present in seawater, just in extremely low concentrations. Every time a river flows to the ocean, it brings dissolved minerals from the land. Hydrothermal vents add elements from deep in the Earth's crust. Atmospheric dust falls on the ocean's surface. Over billions of years, the ocean has become a dilute solution of everything, a liquid that reflects the entire periodic table in its chemistry. This chemical diversity is part of what makes the oceans so important to life. These dissolved elements provide the raw materials that living organisms need to build their bodies, from the calcium in shells to the iron in blood cells. When we think of oxygen production, we usually think of forests and plants on land, but actually more than half of the oxygen in Earth's atmosphere comes from the ocean. Single-celled organisms called phytoplankton drift in the sunlit surface waters, using photosynthesis to convert carbon dioxide and water into sugars and oxygen, just like plants do on land. These microscopic organisms are so abundant and so productive that despite their tiny size, they collectively produce more oxygen than all terrestrial plants combined. Every second breath you take comes from the ocean, from phytoplankton you'll never see, doing their quiet work in the sunlit layer. Prochlorococcus, possibly the most abundant photosynthetic organism on Earth, is so small that a thimbleful of seawater might contain 100,000 individuals. These tiny cells, barely visible under a microscope, are fundamental to life on Earth, the base of the marine food web and a primary source of the oxygen that makes our atmosphere breathable. Just as avalanches can rush down mountainsides on land, avalanches occur underwater when sediment on steep slopes becomes unstable and begins to slide. These underwater avalanches, called turbidity currents, consist of sediment-laden water that's denser than the surrounding clear water. They can be triggered by earthquakes, storms, or simply by sediment accumulating until the slope fails. Once moving, turbidity currents can travel at speeds up to 50 miles per hour, flowing down submarine canyons and across the abyssal plain, sometimes continuing for hundreds of miles. These currents have enough force to snap submarine communication cables on the seafloor. Over millions of years, turbidity currents have carved the submarine canyons that cut through continental margins, and they're responsible for depositing much of the sediment that forms the abyssal plains. They represent one of the main ways sediment moves from shallow water to the deep ocean, sudden rushing events that briefly transform the usually still deep water into a churning mixture of water and suspended material. While we often talk about the ocean as if it's uniform, salinity actually varies considerably in different places. The open ocean typically has a salinity of about 35 parts per thousand. That's 35 grams of dissolved salts in every kilogram of seawater. But near river mouths where fresh water dilutes the ocean, salinity drops. In polar regions where ice melts in summer, salinity decreases. In tropical areas with high evaporation and little rainfall, salinity can be higher. The Red Sea and Persian Gulf, being warm and surrounded by deserts, have salinities around 40 parts per thousand. The Baltic Sea, receiving outflow from many rivers, has salinity around 8 parts per thousand in places. And the Dead Sea, despite its name not actually part of the ocean, has salinity over 300 parts per thousand, so salty that only specially adapted bacteria can survive there. These variations in salinity affect water density and circulation, creating some of the driving forces for ocean currents, each body of water maintaining its own character determined by evaporation, precipitation, and freshwater input. In a normal kitchen, water boils at 212 degrees Fahrenheit at sea level pressure. But boiling point changes with pressure. In the mountains where air pressure is lower, water boils at a lower temperature. In a pressure cooker, water can be heated above its normal boiling point without turning to steam. The same principle operates in the deep ocean, where the immense pressure raises water's boiling point dramatically. Near hydrothermal vents, where water emerges at temperatures of 700 or even 750 degrees Fahrenheit, the water doesn't boil into steam because the pressure at depth, hundreds of atmospheres, keeps it liquid. If you could somehow rapidly bring that superheated water to the surface, it would flash boil explosively as the pressure dropped. This is one reason why the deep ocean can support the unusual chemistry around hydrothermal vents. Reactions that would be impossible at surface pressure become possible in the high-pressure environment of the deep seafloor, allowing water to exist in states we never encounter in everyday life. Water has a high specific heat capacity, meaning it takes a lot of energy to change its temperature. The ocean, containing so much water and being so deep, can store enormous amounts of heat without warming much. In fact, the ocean stores roughly 1,000 times more heat than the atmosphere above it. This gives the ocean tremendous inertia in the climate system. It heats up slowly and cools down slowly, moderating temperature changes and making coastal areas less extreme in temperature than inland regions. The ocean has absorbed more than 90% of the extra heat trapped by greenhouse gases in recent decades, slowing the rate of atmospheric warming but warming the ocean in the process. This stored heat will continue affecting climate for decades or centuries, even if greenhouse gas emissions stop, because it takes so long for the ocean to release heat back to the atmosphere. The ocean acts as Earth's thermal battery, storing and releasing energy on timescales far longer than the atmosphere's rapid fluctuations. When wind blows across the ocean surface, friction transfers energy from the air to the water, creating waves. Initially, these are small ripples, but as the wind continues blowing, the waves grow larger. The size of waves depends on 3 factors: wind speed, how long the wind blows, and the fetch, the distance over which the wind blows across open water. Strong winds blowing for days across thousands of miles of ocean can create massive swells. Once formed, these swells can travel thousands of miles from where they originated, moving as organized patterns of energy through the water. This is why you can have large surf on a California beach from a storm that occurred near New Zealand, or why the coast of Portugal receives swells generated by storms in the North Atlantic. The waves arriving at a beach might carry energy from wind that blew days ago and thousands of miles away, the ocean storing and transmitting that energy across vast distances with remarkable efficiency. Earth rotates, and this rotation affects moving fluids like water and air. In the northern hemisphere, moving water deflects to the right of its direction of travel. In the southern hemisphere, it deflects to the left. This is called the Coriolis effect, and it's why hurricanes spin counterclockwise in the north and clockwise in the south, and why ocean currents curve in great loops called gyres rather than flowing straight. The Gulf Stream, for example, flows north along the US coast partly because of the Coriolis effect, deflecting the water to the right, pushing it against the coast. Without Earth's rotation, ocean currents would flow directly from high pressure to low pressure, but the Coriolis effect turns them, creating the circular patterns we observe. This effect is stronger at higher latitudes and weaker near the equator, influencing everything from weather patterns to the distribution of nutrients in the ocean. a consequence of living on a spinning planet with a fluid surface. Pure water freezes at 32 degrees Fahrenheit, but adding salt lowers the freezing point through a process called freezing point depression. The dissolved salt interferes with the formation of ice crystals, requiring a lower temperature before the water can solidify. Typical ocean water with a salinity of 35 parts per thousand freezes at about 28.4 degrees Fahrenheit, though this varies slightly depending on exact salinity. This is why the ocean can be so cold in polar regions without completely freezing over. The water remains liquid at temperatures below the freezing point of fresh water. When seawater does freeze, the ice that forms is actually much less salty than the water it formed from, because the ice crystals exclude most of the salt, leaving very salty brine behind. This brine is denser than the surrounding water and sinks, contributing to deep ocean circulation. The salt in seawater thus affects not just its freezing point, but the entire process of ice formation and the circulation patterns that result. Despite centuries of ocean exploration, scientists are still discovering new species at a remarkable rate. Roughly 2,000 new marine species are formally described each year. These discoveries range from microscopic plankton to fish, invertebrates, and even occasionally larger animals. Some are found in the deep ocean, in places humans have only recently developed the technology to explore. Others are in shallow water but are rare, small, or well camouflaged. Some have been in museum collections for years but only recently identified as new to science. This constant discovery reminds us how incomplete our knowledge of ocean life remains. Every expedition to deep-sea vents or seamounts typically finds species never before seen. Genetic analysis reveals that organisms we thought were one species are actually several closely related species. The ocean continues revealing its biodiversity slowly, each new discovery a reminder of how much remains unknown. How many creatures live their entire lives in waters we've never adequately explored, unnamed and unclassified? For decades, this was straightforwardly true. We had better maps of the Moon and Mars than of our own ocean floor. We've mapped the entire surface of Mars using orbiters, though at varying resolutions. We've also mapped 100% of the Moon. With modern sonar technology and efforts like the Seabed 2030 project, we've now mapped about 25% of the ocean floor at high resolution, a significant improvement from the 10% mapped a decade ago. However, the comparison is nuanced. We have better visual imagery and surface detail for Mars and the Moon, because there's no water in the way. The best ocean floor maps use sonar to measure depth, which provides less visual detail than a camera would. We can see what the surface of Mars looks like in stunning detail, while even our best maps of the ocean floor are mostly data about shape and depth, not direct visual observations. The ocean floor remains largely unexplored in terms of what actually exists there, what creatures live there, what the seafloor surface actually looks like up close. Around hydrothermal vents and cold seeps, entire ecosystems exist that don't depend on photosynthesis and sunlight at all. Instead, they're based on chemosynthesis, the process of making food using energy from chemical reactions. Bacteria living near these vents can metabolize hydrogen sulfide or methane, compounds that would be toxic to most life, and use the energy released by these chemical reactions to produce organic molecules, just as plants use sunlight to produce sugars through photosynthesis. These bacteria form the base of the food web around vents. Tube worms, mussels, and clams have formed symbiotic relationships with these bacteria, hosting them in their bodies and living off the nutrients they produce. These ecosystems represent a completely different approach to energy, life that could in theory exist on other worlds that never receive sunlight, communities that show the remarkable flexibility of biology, finding ways to extract energy from Earth's internal heat and chemistry rather than the sun. Since the mid-20th century, scientists have documented a concerning trend. Populations of phytoplankton, those microscopic photosynthetic organisms that form the base of the marine food web and produce much of Earth's oxygen, have declined by roughly 40% globally. The reasons aren't entirely clear, but climate change is likely involved. Warming ocean temperatures may be strengthening the stratification between warm surface water and cooler deep water, making it harder for nutrients from below to reach the surface where phytoplankton live. Ocean acidification might also play a role, as might changes in ocean circulation patterns. This decline has troubling implications. Phytoplankton support virtually all marine life, and changes in their abundance can ripple through entire ecosystems. They also play a crucial role in the carbon cycle, absorbing CO2 from the atmosphere. Understanding why phytoplankton populations are declining and what that means for ocean health and global climate is one of the urgent questions facing marine scientists today. On certain reefs, once per year, something magical happens. All the corals release their eggs and sperm simultaneously in a mass spawning event that turns the water milky with reproductive cells. This synchronization is remarkable considering coral are stationary animals attached to rocks. The timing is controlled by environmental cues. Water temperature, length of daylight, and lunar phase all play a role. On the Great Barrier Reef, mass spawning typically occurs 4 to 6 nights after a full moon in October or November when water temperatures have reached a critical threshold. When it happens, it's spectacular. Millions of tiny pink and orange egg bundles rise through the water, creating an underwater snowstorm in reverse. The synchronization increases the chances of fertilization and may overwhelm predators. So many eggs are released at once that predators can't possibly eat them all, ensuring some survive. This event demonstrates how living communities can coordinate across large scales using shared environmental signals, the entire reef spawning together in the dark water. When we think about life on Earth, we tend to think about the species we encounter on land: mammals, birds, trees, insects. But the vast majority of Earth's living space is in the ocean, and most of Earth's biomass and biodiversity is marine. The ocean, from the surface to the deepest trenches, from coral reefs to abyssal plains, contains an estimated 50 to 80% of all life on the planet. Most of this is microbial, bacteria and archaea living in the water and in seafloor sediments, but it includes an incredible diversity of multicellular life as well. There are more phyla of animals, major body plans, in the ocean than on land. The ocean is where life began, and it remains life's primary home, containing more living organisms, more biomass, and more diversity than all terrestrial and freshwater environments combined. Most of this life exists far from shore, in the open ocean and in the deep, places humans rarely visit, continuing its existence largely beyond our notice. The most volcanically active places on Earth are underwater, along the mid-ocean ridges where tectonic plates pull apart and new ocean crust forms. Scientists estimate there are roughly 1 million volcanoes on the ocean floor, and volcanic eruptions are constantly occurring somewhere in the deep ocean. Most of these eruptions go undetected because they occur at depths where no one is watching. Sometimes the only evidence we see is a plume of warm, chemically distinct water detected by research vessels or slight seismic activity recorded on monitoring stations. Unlike dramatic volcanic eruptions on land, most underwater eruptions are relatively gentle, effusive eruptions where lava flows slowly from fissures in the seafloor. The water quickly cools the lava, forming distinctive pillow-shaped structures. This constant volcanic activity is creating new oceanic crust, adding to the ocean floor, a process that has continued for billions of years, the Earth renewing itself continuously in the deep ocean where most of us will never witness it. Sea turtles undertake extraordinary migrations, swimming thousands of miles across open ocean and then returning to the same beaches where they were born to lay their own eggs. How they accomplish this navigation remains somewhat mysterious. Scientists know turtles can detect Earth's magnetic field and may use it like a map, sensing both the field's intensity and inclination to determine their position. They may also use wave direction, ocean currents, chemical cues in the water, and even possibly celestial navigation by sensing light polarization. Young turtles apparently learn magnetic signatures of different locations during their first migration, creating a mental map they use throughout their lives. But the relative importance of these different cues and exactly how turtles integrate them into a navigational system remains uncertain. What's clear is that turtles possess remarkable sensory capabilities and a navigation system sophisticated enough to guide them across entire ocean basins, year after year, finding their way through water that to us looks uniformly blue and featureless. In the cold waters near Antarctica and in the Arctic Ocean, water temperatures can drop below the freezing point of pure water, and with dissolved salts, seawater can remain liquid at temperatures cold enough to form ice crystals in an organism's tissues. Some fish living in these extreme cold waters have evolved antifreeze proteins, molecules that interfere with ice crystal formation by binding to tiny ice crystals as they form, preventing them from growing larger. These proteins allow the fish's bodily fluids to remain liquid at temperatures that would otherwise freeze them solid. Different fish species have evolved antifreeze proteins independently, arriving at similar solutions through different evolutionary paths. The discovery of these proteins has applications beyond just understanding fish. Scientists have studied them for potential use in preserving organs for transplant, preventing ice formation in crops, and improving the texture of frozen foods. Once again, studying seemingly obscure questions about how fish survive in cold water has led to discoveries with far-reaching applications, the ocean teaching us about the possibilities of biochemistry. We've sent rovers to Mars that have driven for miles, taking thousands of photographs and analyzing rocks and soil. We've sent spacecraft past every planet in our solar system, mapping their surfaces and moons in detail. Meanwhile, the deepest parts of our own ocean have been visited by humans only a handful of times, and vast regions of the deep ocean have never been explored at all. The challenges of deep ocean exploration are immense: the pressure, the darkness, the cold, and the difficulty of deploying equipment to such depths. Most of our knowledge of the deep ocean comes from brief visits by remotely operated vehicles or data collected by instruments that sample but don't observe. We can make generalizations about the deep ocean, but specific knowledge, what lives here in this particular place, what this specific section of seafloor looks like, how communities function, remains sparse. The ocean keeps most of its secrets still, especially in the deepest waters, places closer to us than Mars but far more difficult to reach and study. Right now, as you read these words or drift towards sleep, the ocean continues doing what it has done for billions of years. Currents flow, carrying heat and nutrients across vast distances. Waves rise and fall, driven by wind and gravity's pull. Creatures hunt and hide in the darkness of the deep. Phytoplankton photosynthesize in the sunlit surface, producing oxygen that will eventually reach the atmosphere. Whales sing songs that echo through the water. Coral polyps extend their tentacles to feed. The ocean breathes in and out with the tides. It circulates through its great conveyor belt. It absorbs heat and carbon from the atmosphere. It supports life in forms we know and forms we've never seen. The ocean doesn't need us to watch it or understand it. It simply continues, patient and vast, holding its mysteries in the dark and the deep, doing its essential work of making this planet habitable. And we get to rest knowing the ocean is out there, the largest part of our world, still mostly unknown, still full of wonder, still operating on timescales and scales that humble us. The ocean will be there tomorrow, and for all our tomorrows, continuing its ancient, patient rhythms while we sleep and wake and sleep again. The ocean holds so many mysteries still, waiting in the cold and pressure and darkness, places we may never visit with our own eyes but can appreciate with our minds and imaginations. These 100 mysteries are only a beginning. The ocean contains thousands more, millions more. Questions we haven't thought to ask and wonders we haven't dreamed of yet. And that's all right. The ocean doesn't need to be fully known to be beautiful and important. It can simply continue being what it is, vast and deep and alive and patient, doing its work while we rest.